Thank you everyone for coming to my presentation. As you can see, I'm going to talk about suppression of spurious signals in thermal MEMS gyroscope. I will start my presentation with a brief description regarding the principle of thermal MEMS gyroscope operation, and then I will talk about the spurious signal in the gyro's output and our observation to our simulation results and also the experimental results. Then I will go through simulation model, which is a two-dimensional model which is built in COMSOL CFD package, and I will continue my presentation with a proposed solution for suppression of this spurious signal in the output of gyro, which can be done by separating the corridors from buoyancy. And finally, conclusion. Talking about this device, I would like to mention that this device was invented by my supervisor in Simon Fraser University, and this is a device with a fairly simple structure, and unlike most of the commercial gyro in the market, this device doesn't have any vibrating solid proof mass, and so instead the Coriolis effect will act on an oscillatory gas stream. As you can see in phase 1 in this figure, this moving gas is created by two heaters which are located symmetrically with respect to the right temperature sensor and the left temperature sensor. So when one of the heaters is here in phase 1, when bottom heater is it's on, the gas around the heater heats up and expands. And when there is no angular rotation, this gas is moving in a symmetrical path, and so no differential temperature is detected as a result. The same scenario is in phase 2, but the only difference is that the direction of the moving gas is changed, but still the differential temperature is 0. Okay, but when this device is rotated, this moving gas, the hot gas around this heater, is moving toward one of the sensors as the Coriolis acceleration will act on the gas, and so it will give us a positive differential temperature, and in the next phase we will go through the same scenario, but the direction of the moving gas is changed, so we will get a negative differential temperature. By reversing the polarity of the differential temperature with respect synchronous with the switching of the heater, we can get an output signal which is proportional to the rotation and also the direction. So this is the principle of this device. Here in this slide, I just want to show a simple structure of this device. The temperature sensors and the heaters, as you can see, and the right picture is the fabricated device, which is fabricated in microfabrication facilities in Simon Fraser University. But okay, what is this spurious signal that I'm talking about, and from where it comes? The ideal behavior which I was talking about is only valid when this device is unaccelerated or it's lying horizontally. But here you can see the experimental results. When we were collecting these results, we didn't rotate the device at all. Like, this device were completely stationary. In the left figure, you can see that the device is located with 90 degrees with respect to the gravity vector, and what we see that we get almost no differential temperature in the output, which as we expected. But here in the right figure, when we switch from 90 degree to 45 degree, we get an alternating signal which is so similar to the rotational signal. And so this way we cannot distinguish if this is the rotational signal or what we call it a spurious signal. But here we know for sure which this is not rotational signal, because this device, this data is collected when the device was stationary. So if I want to explain that in a simple way, I decided actually to split the device in two. So to show that how is the position of the heaters, the top heater and bottom heater. We realize that the buoyancy of the heated gas creates convection currents, that the position of these currents is changed when the power is switched from one heater to the other one. So as a result, these convection currents will strike the sensors at different positions. And as a result, we get this, what we call it, a spurious signal in the output of our gyro. And we refer to this as geometric effect. What I want to talk about that here is, because this is a varying bias, we cannot get rid of this acceleration signal or a spurious signal in the output, because by the detection timing which I was talking about in the second slide, it was a constant bias. We could do that easily. It was so easy to do that, but because it's varying, it's a varying bias, it's difficult to get rid of this signal. Okay, in order to reproduce the experimental results, we had to make a model, and we built this model. It's a two-dimensional model in COMSOL CFD package. And the interesting point is that although COMSOL provides natural convection module, but unfortunately we couldn't use this module because the main principle of gyro operation here is due to the expansion of gas because of the heated gas. And so COMSOL employs Bosenisk approximation. So, and as a result, we couldn't use that because it cannot represent the phenomena that I was talking about, because the main principle of gyro operation is due to the creation of gas currents by the expansion of heated gas. Here you can compare the simulation result with the experimental result. As you can see, they are in almost good agreement with each other. And so when I was doing the simulation, I was switching off the rotation. Here we just have acceleration, 1g acceleration, and I just tilted the device for 45 degrees. And as you can see, we got almost the same as the experimental results. So right now we know that we are in the right track. So we know what is the problem, and we have to find the answer for that, what we should do, the solution. One way that we can do that is that we can solve this problem is that we have to separate the Coriolis from the buoyancy, and this can be done, but it seems to be difficult because the most governing parameters for these two forces are the same, and so that's why this is a difficult task to do. The only difference that I can talk about here is that the buoyancy flow is a steady state flow, and so it depends on how hot the gas gets. So how hot the gas is compared to the ambient temperature, the gas inside the device and the ambient temperature. And the rotational signal, it's a transient signal, so it depends on the time. So it corresponds that how fast it gets hot. This suggests us that if we look at a smaller gyro with a higher switching frequency, we might see that both the buoyancy signal and the rotational signal will get a smaller, but perhaps buoyancy signal will get a smaller faster. So before going through the simulation result and see the signal to noise ratio for a smaller gyro and with higher switching frequency, I just want to make it clear what we refer to noise and signal here. Noise for us is the signal that we get due to acceleration of 1g, and the signal is due to revolution of due to the rotational the amplitude of rotational signal due to 1 revolution per second. So what we did here, we just decreased the cavity, the size of the cavity, because we get less volume of gas, and as a result, the time which takes for the gas to reach 90% of equilibrium temperature will be much smaller. So we decreased the size by 25% and 50%, and then we compared the signal to noise ratio for different switching frequency. But the point is here that there is a maximum for sure for defining this switching time, because every heater should be on enough to reach 90% of equilibrium temperature in the cavity. So here you can see the experimental result. As you see, the best result that we got is for a gyro with 50% size of the original one that we have, with a length of 0.75 millimeter, because the original one has a length of 1.5. And with a switching frequency of 350 radian per second, we get almost a ratio of 10. But looking at the absolute sensitivity at the same time, you can see that the sensitivity is also getting really low. So this is a drawback of this approach, and it seems that we get a small differential temperature, which is almost it's not detectable. So for conclusion, we know that we have to suppress this spurious signal in order to detect the rotational signal in the gyro's output, and through our simulation we showed that by increasing the switching frequency and decreasing the dimension, we could get a signal to noise ratio up to almost 10. But at the same time, the drawback is that the sensitivity is decreased. This research is still in progress, so we hope that in the near future we can also increase the sensitivity. Thank you, and any questions?